Jai Hind everyone. Myself Dr. Vani Bharg, Associate Professor in EN Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today in this lecture, I am going to discuss about the controlled converters, the classification of the converter, and I will start the single phase half wave converter as well. This is in the subject of power electronics. As per the AKTU syllabus, it is KEE 603 Unit 3. So, controlled rectifiers or controlled converters. Controlled rectifiers are line commutated AC to DC power converters which are used to convert a fixed DC voltage, fixed frequency AC supply into a variable DC voltage. If we can see the same can be seen from this block diagram representation of the same. Here we can see that this block is actually representing a line commutated converter. The input to this line commutated converter is AC input and the output of this line commutated converter is DC output. In this case, we are discussing the controlled converters or controlled rectifiers. So, DC output is going to be variable in nature. So, we can define that type of input for these kind of converters is the fixed voltage, fixed frequency AC power supply, and the type of output that we are going to obtain is the variable DC output voltage of the converter available across these two output terminals of the converter. Various applications of the phase control rectifiers are DC motor control, in AC fed traction system using DC traction motor, in electrochemical and electrometallurgical processes, in magnet power supplies, in reactor controls, portable hand tool drives, variable speed industrial drives, the battery charging system, the high voltage DC transmission, and UPS, that is uninterruptible power supply systems. They all actually require the variable DC supply. So, the application, the phase control converters find application at these places. Let us now classify the phase controlled converters. The classification can be seen to be like this. We have single phase control rectifiers. Of course, they operate at from the single phase AC supply. We have three phase control rectifiers which operate from three phase AC supply. So, in general, we have two kinds. Depending upon the type of supply, the converters can be classified as single phase converters and the three phase converters. Among single phase converters, we are going to have various types. Likewise, among three phase converters, we are going to have various converter circuits. So, let us talk about the different types of single phase controlled rectifiers. We have the half wave controlled rectifier, we have the full wave controlled rectifier. The half wave control, the single phase half wave controlled rectifier actually uses a single thyristor which provides the output control only in one half cycle of the AC voltage. And the full wave control rectifier, it provides the control in both the half cycles. We have got two configurations of the same. We have got single phase full wave control rectifier using a center tape transformer. The center tape transformer, this particular configuration is said to be the midpoint configuration. It is midpoint configuration. And the other configuration is bridge configuration. The midpoint configuration requires a secondary center tape transformer and it requires two controllable switches. In our case, we are going to use the controllable switch we are going to use is an SCR or thyristor. The full wave bridge control rectifier requires 4 such SCRs. It doesn't require any secondary center tape transformer. The full bridge converter configuration may be a single phase semi converter or it may be a single phase full converter. The single phase semi converter, in single phase semi converter, it is actually a half control bridge converter using 2 SCRs and 2 diodes in addition with 2 SCRs. The single phase semi converter or the half wave controlled converter actually provides operation in single quadrant only. Likewise, we are having single phase full converter. It is the fully controlled converter, and the fully controlled converter is capable of providing two quadrant operation. We will discuss the quadrant as well as operating quadrant of various converters as well. In the similar manner, different types of three-phase control rectifiers are, we are having three-phase half-wave control rectifier, we are having three-phase full-wave control rectifier. The three-phase full-wave control rectifier, we may have the midpoint configuration as well as the bridge configuration. Here, what I have mentioned is the types of the bridge configuration only. We may have the semi-converter or full converter, just like we had the semi-converter and full converter with single phase supply. A three-phase bridge actually requires three switches or three SCRs. If we are talking about the semi-converters, three-phase semi-converters or three-phase half-control converters, this converter is going to have three SCRs along with three diodes. If I am talking about the three-phase full converter, it is going to have three SCRs. The three-phase semi-converter will provide two quadrant operation, single quadrant operation I mean to say, and three-phase full converter will provide two quadrant operation, right? So, semi-converters provide single quadrant operation and full converters provide two quadrant operation. Now, when I am saying quadrant operation, it means I am talking about the VI plane. Suppose this is the VI plane. If I am having current over here and voltage over here, over horizontal axis I am having current, over vertical axis I am having voltage, then quadrant 1 operation means the output voltage, the average output voltage and average output current are only going to be positive throughout the operation of the converter for entire operating range of the firing angle of the converter. If I am talking about two quadrant operation, then in control rectifiers, the meaning of two quadrant operation is, as far as this is concerned, the meaning of two quadrant operation is, I am going to have operation in first quadrant and in the fourth quadrant. The operation in fourth quadrant means we can have a negative average output voltage but with positive current, right? So, I can have the operation of the converter either in the first quadrant or in the fourth quadrant. In first quadrant, average output voltage and current would be positive. In fourth quadrant, average output voltage would be negative, whereas average output current would be positive. If suppose I draw it differently, if suppose I draw it in this manner, if I am taking V0 over the horizontal axis and I0 over the vertical axis, then these converters, the two quadrant converters, that is the full converters, say for example, it will operate in first quadrant and in the second quadrant. So, always keep in mind what you are having over x-axis and over the vertical axis. Now, let me discuss, but before going through the phase control, principle of phase control, let me tell you another criteria, another classification of these converters. We can classify, right now I have given you the converter classification based upon the type of input supply, single phase supply or the three phase supply. Besides this, converters can also be classified depending upon the operating quadrant in which those converters can be operated. So, as per this classification, I can classify these converters as single quadrant converter. I can have two quadrant converter and I can have four quadrant converter. These phase controlled converters can operate with positive voltage, positive current. If I am talking about two quadrant converter, that is actually positive voltage, positive current and negative voltage, negative current. If I am talking about four quadrant converter, it means I can have operation in all the four quadrants. Operation in all the 4 quadrants means I can have either positive or negative voltage and I can have either positive or negative current. To obtain a 4 quadrant operation, actually we need to connect 2 full converters back to back, then only 4 quadrant operation of the converter is possible. So, I have told you about 2 types of classifications. The first type was based upon the type of the supply that we are giving as input to the converter. The second classification is based upon the number of operating quadrants in which my converter is operating. There is another way of classifying the converters. It is based upon the number of pulses of the output voltage in one complete cycle of the input voltage. So, depending upon this, I can classify the converters as single pulse converter. I can have 2 pulse converter. I can have 3 pulse converter. I can have 6 pulse converter. I can have 12 pulses converter as well, but again our 12 pulse converter is actually going to be the connection of 2 6 pulse converters. So, let us try to understand what is the meaning of single pulse converter. Single pulse converter means in one complete cycle of the input voltage, the total number of pulses obtained in the output would be equal to 1. What does it mean? If suppose this is the supply, the input supply, in the output, this is the entire duration of this input supply. You know that it is equal to twice pi radians. In this twice pi radians, if I am getting 1 pulse in the output voltage, then this type of converter is said to be a single pulse converter. I hope you can understand the meaning of this. You can relate it with a converter. A simple single phase half wave converter actually provides the single pulse output, right? So, a single pulse converter, then comes the 2 pulse converter. A 2 pulse converter is the converter in which in one complete cycle of the input voltage, we are going to have 2 pulses of the output voltage, right? The example is single phase full wave converter. Then comes the 3 pulse converter. In 3 pulse converter, in one complete cycle of the input voltage, we are going to have 3 pulses in the output voltage, right? Likewise, in 6 pulse converter, in one complete cycle of the input voltage, we are going to have 6 pulses of the output voltage. So, whenever we will discuss any type of converter, I'll discuss the operating quadrant and the number of pulses that we are getting in the output voltage as well. So, keep it in mind. Keep this classification in mind as well as this classification in mind. We will keep on recalling them while discussing various converter circuits, right? So, now let us start with the principle of phase control rectifier with the help of a half wave controlled converter. This is the simplest circuit of a converter, and here for further simplifying the operation, I am considering the presence of purely resistive load at the output terminals of the converter. So, what do we have in this converter? You can see the way of seeing any circuit is to see it in partitions, in portions. In every converter circuit, if you see, there are 3 portions actually, 3 sections actually. The very first section is the supply section, the last section is the load section, and the middle section is actually the converter circuits. So, as far as this circuit is concerned, what you can see, This is the first section, this is the second section. For simplicity only, I am explaining the converter. I am just trying to explain you the construction of this circuit, the configuration of this converter circuit in the form of 3 sections. Any converter circuit can be seen in 3 sections only. You are always going to have the first section as the supply section, the last section as the load section, and the middle section is going to be your converter section. Let it be any kind of converter, let it be an AC to DC converter, let it be a DC to DC converter, let it be a DC to AC converter, or let it be an AC to AC converter. In every type of converter circuit, the first section is always the supply section, the second section is the converter section, and the last section is the load section. Actually, what is the purpose of a converter? The purpose of any kind of converter is to provide a controlled supply to the load, right? Fixed supply is available from the supply. We need to provide a variable supply to the load depending upon the requirement of the load, right? So, in between we have inserted a converter section. The purpose of converter section is to control the power that is being provided to the load from a fixed supply. So, as far as this circuit is concerned, what you can see at the input side, you can very well see the presence of an AC source. So, this voltage is defined as Vs equals to Vm sin omega t. I hope you understand the meaning of this equation. Small Vs is representing the instantaneous value of the supply voltage. From here, you can see that supply voltage is sinusoidal in nature with a peak value of Vm. So, supply voltage is sinusoidal with a peak value of Vm. This is Vm. This is the negative half cycle of the supply. This is pi. This is 2 pi. The x-axis is the axis of the angle or omega t or theta or of time. Vertical axis is the axis of the source voltage Vs. So, this is the representation of a single phase AC supply with 0 phase angle delay, right? Now, let us see the voltage across the load. Let this voltage be some voltage V0. This is going to be the positive polarity of the voltage, and this is going to be the positive direction of the current flowing in the load circuit. In between, we are having, as the converter, we are having a single thyristor present over here. The voltage drop across thyristor, we know that this is the anode terminal of the thyristor, this is the cathode terminal of the thyristor. We also know that this is the gate terminal of the thyristor or SCR, and the polarity of voltage across SCR would be positive side at anode and negative side at the cathode. So, plus minus VT1, where T1 is the thyristor, T1 is the thyristor. So, VT1 is representing the voltage across this particular thyristor. The operating quadrant of this converter is shown to be the quadrant 1. Quadrant 1 means the average output voltage as well as the average output current, both will remain positive only. We cannot have, with this type of circuit configuration, we cannot have a negative voltage output across the load terminals of the converter, right? Now, let us try to understand the operation of principle of operation of this circuit. To understand the principle of operation, we must know that when a thyristor is forward biased, a thyristor or SCR, I am actually talking about the SCR. Thyristor term is used for the SCR, right? And this must be known to you well. So, you must know that when a thyristor is forward biased, let us first try to understand the meaning of forward biasing of the thyristor. Thyristor is said to be forward biased when its anode terminal is at positive potential with respect to its cathode terminal, right? So, during positive half cycle of the source voltage, let us assume that during positive half cycle, suppose we have got two terminals, let it be terminal 1, let it be terminal B, terminal A and terminal B. So during positive half cycle of the source voltage, assuming that terminal A is positive with respect to terminal B, as this is an alternating supply. So you know, during positive half cycle we are going to get one polarity of the voltage supply, and during negative half cycle we are going to get the second polarity of voltage, opposite polarity of voltage supply. So during positive half cycle, terminal A is positive with respect to terminal B, making the thyristor T1 forward biased, right? Now, depending upon the requirement, suppose we are triggering the thyristor T1 at certain firing angle alpha, right? Thyristor becomes forward biased at this instant, just after this. What is this? This is omega t equals to 0. This is actually the positive zero crossing of the supply voltage. You must be aware of the positive zero crossing and negative zero crossing. The zero crossing after which the voltage becomes positive is said to be the positive zero crossing, and the zero crossing after which the voltage becomes negative is said to be the negative zero crossing. So, what you can see over here is, just after omega t equals to 0, that is after the positive zero crossing of the supply voltage, thyristor T1 would be forward biased. Thyristor T1 would be forward biased means the anode is at positive potential with respect to cathode, making the thyristor to be forward biased after certain delay angle of alpha, where alpha is said to be the firing angle or triggering angle of SCR. So, after certain delay angle alpha, we will trigger thyristor T1. What happens with triggering of thyristor T1? What happens with triggering of thyristor T1? Let me redraw the source voltage waveform with more clarity to explain you what is actually happening to the thyristor when it is triggered. Here, I have drawn only the single cycle of the source voltage, right? To show the gate current over the same axis, let me just change the color of the ink. So, along with Vs, I am also marking the gate current for the thyristor. Suppose at certain angle alpha, I am providing a gate trigger pulse for triggering of the SCR T1. What happens when I provide a trigger signal for triggering of thyristor T1 or SCR T1? It will turn it on. What happens when this gets turned on? Turning on of thyristor causes short circuiting of this portion, right? When thyristor gets turned on, it behaves like a closed switch, right? A switch in closed state behaves like a short circuit. In ideal case, the resistance of this switch, the on state resistance offered by this switch would be 0. In practical case, some very small amount of resistance is offered by the switch in its on state, right? So, thyristor behaves like a short circuited switch. What happens? This is short circuited. What was the polarity of voltage here? Plus here, minus here. In between, we have got a short circuit. The same source voltage will appear across load as the load voltage during this positive half cycle, right? I can very well plot the voltage appearing in the load circuit. It is the same positive half cycle, but it starts appearing across the load only after thyristor T1 gets triggered, right? So, thyristor T1 gets triggered at this particular instant of time denoted by alpha. I'll get this much amount, this to be the output voltage waveform across load. So, from alpha to pi, I'm getting the output voltage, right? What about the output current? When load gets connected across the source, the current starts flowing. This is the load current I0. The instantaneous value of load current I0 can be written as V0, instantaneous V0 divided by R. Instantaneous V naught divided by R can also be written as instantaneous Vs divided by R. Why so? Because the load voltage is nothing but the source voltage only. Assuming zero voltage drop across the conducting switch, across the conducting SCR, the output voltage is same as the source voltage. So current I naught can be written as Vm sin omega t upon R. I hope you agree, right? What is the variation of the waveform of current I naught? Same as the waveform of the voltage. Why so? Because we have got resistive load. With resistive load, there is no variation as far as the shape of the waveform is concerned. So what about the load current? The load current is going to remain same as the source voltage or the load voltage, I must say. So this is current I naught. From alpha to pi, the current is flowing in the circuit, right? From, let us see what happens at omega t equals to pi. Let us see what happens at omega t equals to pi. At omega t equals to pi, voltage is at its negative zero crossing. Voltage, source voltage reduces to zero value. So load voltage is also at its negative zero crossing. And hence, as the current is following the variation of the voltage only, so current also reduces to the zero value at omega t equals to pi itself, right? Now, you just recall, when current flowing through an SCR reduces below the holding value of current, the SCR gets turned off, right? For complete turn off of the SCR, just after reduction of this current to zero value, a negative voltage should appear across the SCR, right? So what is happening at omega t equals to pi? Naturally, because of natural variation of the voltage, current is reducing to its zero value, right? What happens when current is reducing? Current got reduced to its zero value at omega t equals to pi. Just after omega t equals to pi, what is the polarity of the voltage? The polarity of the source voltage is plus here, minus here. I hope you agree, right? What does it mean? A negative voltage at the input side is causing reverse biasing of the thyristor. So just after reduction of current to zero value, a reverse voltage gets applied across the thyristor because of the natural variation of AC supply voltage. Thyristor will get completely turned off, right? What about the load circuit? Thyristor is in off state now. Off state means an open circuit. What is the meaning of this open circuit? Open circuit means there is no connection between the load and the supply. So the voltage across load, there would not be any voltage across load and no current is flowing in the load circuit, right? So during this period of time, the load voltage as well as load current will remain zero. After that, repetition of the same pattern will take place during next positive half cycle, during next negative half cycle, and so on, right? The complete waveform are drawn over here. This is the source voltage, which I have already told you. This is the voltage appearing across load, that is the load voltage. This is the variation of load current with resistive load, and this is the voltage across the SCR. Keep it in mind that whenever SCR is blocking the voltage, that voltage will appear across the SCR. SCR is blocking the voltage during positive half cycle before just before triggering of the SCR. So from 0 to omega t equals to alpha, SCR is blocking the source voltage. So source voltage as it is will appear across the SCR, right? After that, from pi to 2 pi, the SCR is reverse biased by the source voltage. So same source voltage, negative half cycle, will appear as reverse voltage across the SCR, right? So that's all for this lecture. I'll continue in the next lecture beyond this point. Over the point topic of discussion will remain same, that is single phase half wave rectifiers. Thank you.